My name is Franjo. I'm from Veski. I work for now more than 15 years in Veski and doing machine condition monitoring. And I had to step in the last moment instead of my colleague Hussein. He got a baby recently, so we had an unexpected situation. I was hoping my boss will present this, but I got offer I couldn't refuse, so I will try to explain this as much as I can. And for all the further questions, Hussein and other will try to provide more detailed answers if someone has. Maybe just to start with questioning to get the feeling about the audience. Who has the experience about machine learning? Or you are the mainly hydro guys? I see one hand, two hands. Okay, and the others are mainly hydro guys. Okay. So we started machine learning, I would say like 4 years ago in Veski. And why we did it. So till now we are doing conventional, traditional condition monitoring for many years. And the goal is to try to detect a fault as early possible. As you are mainly coming from the hydro sector, you understand why it's important. So you can plan maintenances, you can prevent faults, so it's easier to repair the machine and so on. So that's like holy grail, to detect the fault as early as possible, so it's easier and cheaper to fix it. Of course, it's only the goal. In the practice, it's not so easy, and especially when you have a human who is analyzing all the data, it is more person dependent. So idea is to create a system that is more robust, that is not reliable on the occurrence of the fault checks, and to make it automatic to run. So first of all, we are doing like online monitoring. That's the basis of everything. You have to measure something to be able to provide some data inputs for the machine learning. Usually, online monitoring has limited set of sensors, and for the machine learning and all other analysis, not only for the machine learning, also for the expert analysis, it's much better to have more informations that you usually get with the integration with already existing systems. So you probably, in most of the cases, you already have some temperature, some pressure, some water flow, and similar measurements in the system. And of course, it doesn't make sense to measure it twice. If you have like some temperature probe and you already have this data in the SCADA system, you will integrate it with some protocols. Modbus, TCP/IP, recently OPC UA, or some other protocol that you already have. And then those two things integrate into one data set that you later on have as an input for your analysis. So on this, until now, we are doing like some asset analytics and performance where we extract different features. So from all those sensors, we will calculate, you know how the trigger sensor looks like. It provides pulse per rotation, so it's one pulse. But that's not information you want. You want to calculate what is the RPM. Also from the proximity probe, you will get shape of the relative vibrations, but you're interested in the peak to peak, in the first harmonic and everything. So you perform the feature extraction that you later on use as an input, and then with all these inputs you can create your machine learning system that can provide some smart notification, predictions, and so on. So what kind of sensors? First of all, you cannot measure everything. You have to choose what to measure. One of my colleagues, more experienced than me, once told me, you have to know what you're measuring. You cannot measure everything, you cannot store everything, you have to pinpoint to things that are critical for you, that are like maybe standard measurement set defined by the ISO standards or similar norms, or based on your experience. If you hear something or if something breaks, you want to focus on that specific part and you want to measure more things around that. So a standard set will have like relative vibrations, absolute vibrations. Vesky is very proficient in the air gap measurements. You will have magnetic flux. You will have axial measurements, and this what I mentioned already. You will have some pressures, flows, temperatures, active and reactive powers, very, very important for all the diagnostics. Load angle as a very specific parameter. So you define your set. If you have a wrong set, you will have garbage in, and you will have garbage out for that. It's not related to the machine condition monitoring and machine learning only. It's about general diagnostics. You need to have good data sets and you need to have proper feature extraction from all those sensors. Otherwise, you will not be able. And we have a joke in company, you know, when you have a good machine, every monitoring system is good. Only time when you have some failures, you actually figure out if you have a good monitoring system or not. So that's the thing, you know, you have to understand what will be important for you once when you get the problems. Otherwise, you know, everything is good, you know, everything is green and no issues. So you have to select the right data set for the measurements and extract the right features. So yeah, we have like sensors like air gaps and flux. That's something that we also produce in Vesky. Some other sensors like accelerometers, proximity probes, they are like commonly available on the market, and you can outsource it almost everywhere. So a few words about feature extraction. So how it looks like and what we do here. Probably most of you heard about raw data, data acquisition, some kilohertz sampling rates, and so on. So all this defines the parameters for your system. So you have to understand your machine. For example, now on the boot, I received many questions. Oh, you are. I said we are measuring with 2 kilohertz, and some customers are saying, oh, but it's too slow. But then I am saying, okay, this machine is running 125 hertz RPM, so it's 2 hertz. So 2 kilohertz for the 2 hertz machine is more than enough. You know, you don't want to put too much data. It's causing stress for the everything. So you have to understand what you are measuring and what you want to do that. So when you do the data acquisition from each sensor, you will get, let's say, 10 to 50 features that you extract. And let's say for Vesky typical installation, every second you have 1,000 data points calculated continuously. So 24/7, around 1,000 data points based from the whole sensor. So some sensor will provide more data features, some of them less. But important part is that all those features are synchronized, calculated in the same moment, and that allows them to create something that's called vector. We are calculating amplitude, phases, and we are creating condition vector, which describes machine condition in this specific moment. And the beauty of that is that we have reduced few 100,000 data points that were actually sampled every second to only 1,000 points. So that's like talking, if you're talking about 1 gigabyte of data and 200 gigabytes of data. And let's say typical installation will also acquire 10 gigabytes of data per year per unit. They're just approximate. If you calculate that with 200 times more, you will get a few terabytes. each year for each unit, and then it like just creates too much. It creates a lot of data that's later on much harder to handle, transfer, backup, everything. So with this, you get a vector that is defining most of the things that you need in 95% of the cases. And the beauty is you can also go back easily, like 4, 5, 10 years ago, and see what was your machine condition. You don't need to store all the data from every sensor, just store the most important parameters. And that is something that you need to do for every machine condition monitoring system. It's not dependent on the machine learning or or if it's some expert doing or whatever. You need to have right data set, you need to have right features, and you need to optimize it not to have too much, but not too little. So you have to configure it properly to have the right inputs. As slide said, if you have garbage in, you will get most likely garbage out. So, and this is what we do in Vesky for more than 20 years. My colleagues who founded Vesky, they started doing machine condition monitoring in early 2000s. And the architectures of the software that we are doing now are exactly the same as they developed at that time. So no physics change, no mathematics change, nothing. Just the way how we visualize the data, how we access it, and that part is changing, but the data itself didn't change at all. So based on this data and based on the experience, we have prepared 4 different approaches for the machine learning that I will try to explain here. So one of them is high vibration starts prediction. So this is example from the database of the data being stored. And some of you might know this, issue here. So one generator in Croatia, the bulb machine, had an issue that during the start, some starts had like really high vibrations and some of them had normal. And it was a pretty long problem. It was not easy to diagnose it, and a lot of people managed to try to figure out what was the root cause and could not do it. So people that from the site experienced the vibration analysts, they were looking through the data and could not figure out that. So you can imagine that it's not pleasant if you don't know if your machine will start with 35 microns or 125 microns. You know, just start it and you are not sure what's going to happen. Of course, this kind of starts are creating much more stress, and they are deteriorating the machine run. You can like 270 and 150 microns during the normal run. It's completely different change. And how we started doing that? We started, of course, focusing on that startup and trying to analyze everything what was going on in the startup, and no one managed to explain what was actually going on. And then we have expanded the window, and we were like analyzing what's going on before the startup and expanding, not like 10 seconds, but looking like half a minute, and half an hour before that. And it also did not help much. At the end, we started to analyze the previous stop. And there we came to some insights what might cause the issue. And here was the clue where to focus. So after general machine learning task is most of the task is not so interesting and fun. It contains of data cleaning, normalization, labeling. So a lot of the data, even if you have a right data set, you will have some junk inside. For example, you have maintenance, you will remove the sensor, you will have faulty data. Or someone will also do maintenance, hit around the sensor, and you will have some crazy speed calculations which are completely not related to the machine behavior. So all this data needs to be cleaned. That's not very fun part. You just have to go through database and find, okay, this doesn't make sense, this doesn't make sense. Someone has to mark it, and then you have to delete it. If you put that as an input to your system, you will make it much more complicated for it, because there is no additional added value from that info. It's just garbage. So I would say it's almost 70% of the machine learning. You're preparing data preparation, labeling, normalization. For the labeling, you have to understand how are things correlated. So you have to label properly, and for that you need an expert that is vibrational expert. For this you need a data scientist, who will, Hussein, he's like a really great machine learning guy, but he doesn't know much about machines. He is looking everything as numbers. And we tell him, check the S-max. And he writes, okay, S-max is some index 125. And he is, like we have a meeting and he says, oh, 125 had this or that correlation. So it's completely two different type of the profiles and experiences. You need to combine them to be able to do all those tasks. On the machine learning, the machine learning does not understand your physical phenomena. It just is correlating the numbers and checking if there is correlation with some features that you add there. And through many examples and trying, we managed to create data preparation in the way that there was suddenly visible data clustering. So when you were looking like this kind of starts, you couldn't figure out which start will be faulty and which one will be a good one. And this, I don't know exactly, but this, let's say, contains 1 year of data. So 1 year of machine operation, you need to have it stored properly, you have to clean it, and then prepare the data as the input. So you have to start collecting first to be able to implement something, and collect for a few years. In this, when we came to this situation, then, okay, with the applied algorithm, it was possible to detect, okay, this, for example, startup will be a faulty one. With a high vibration, this one will be not. And that was the clue where we focused on. And as a result, we managed to get pretty high predictability. Must admit, I'm not sure what these numbers 21 and 25 showing, but based on this clustering, we had like probability, I would say 80 to 90, even after optimizing above 90% of the prediction, which start will be bad and which will be low. So after we somehow narrow down the issue, we have also expanded the feature extraction. And that's what I was telling in the beginning. We added something that we now trend as a pole position after stop. It is a bulb machine, and you don't know how it will stop. And we added procedure that calculates exactly which pole was, let's say, on which position. And that's something that we really custom prepared for this site, something that we prepared for this very specific situation, and it's kind of hard to replicate it directly as a model. We have like monitoring on the bulb machines, maybe 20 or so machines, and none of them had this same behavior. So in this case, machine learning help us to show us direction, where to go and where to look, how to improve the monitoring system. And after this, we are now able to have a pretty high prediction. And the good thing is now, if you predicted that your machine will start with a high vibration, you can do something. You can change the way how you start it, you hit it, or you have a slow roll for a few minutes, or you change the way how you synchronize. You have the situation under the control. And that's the idea from the whole of the machine condition monitoring in general, and machine learning help us to detect that here. Other example, what we did here was pattern recognition. So we have something what we call its fault matrix, where from these 1,000 parameters that we, let's say, calculate every second, then we write which parameter is mainly influencing which error. For example, if you have like mechanical imbalance, you have to describe, I want to monitor this and that parameter. For example, you will check the first harmonic, how it's behaving before and after the machine starts. And this is something that you again need a vibration expert who will create this matrix, and it takes like, okay, there is a lot of knowledge now with on the internet, and especially with this ChatGPT and other tools, but you need to somehow connect all those data points, and you have to narrow down which points to check for which fault. So yeah, and now based on this, we had a task to detect machine magnetic imbalance. And what was the goal here? So you can this like thing, first of all, you don't need necessarily machine condition to do this for you. You can manually check and can calculate. But if you are thinking about measuring and monitoring hundreds and hundreds of the generators, you typically don't have time to check every machine all the time, and you need some tool that can help you to automate what is actually happening and to get some estimation how your machine is behaving. So what was actually the goal? Actually, the machine learning here is doing the excitation detection pattern. So we are trying to find where the machine was actually excited, and then we are checking what was the condition vector position and situation before the excitation and after. And we calculate the vector here. So it's pretty simple mathematics. After all, you need to calculate all those parameters. That's like your input. You have to know, okay, my machine is here on the nominal speed, no excitation, and the vector is, I'm not sure which one, let's say the orange one. Then when the machine excites, I get the green vector, and result is the red vector. So mathematics is actually pretty simple, but the machine learning help us to automate how to find the points for those vectors. You know, to say, okay, this moment in time was before the excitation, and this was in the excitation. You could do something similar with different methods. You could do it manually, you could do it with some thresholds or different ways. But for us, it was interesting to explore if we can implement some pattern and to detect it here. So this was relatively, let's say, simple task. But those kind of patterns you can define for different parameters, for different situation. For example, we used it here to detect magnetic imbalance. You can use the same approach to detect mechanical imbalance. You would check what is the vector before the nominal speed and after the before running. So you would take this point and this point. You could check what is happening with your let's say rotor shape. You have like air gap monitoring, you have like circularity, concentricity, and other parameters that are defined according to the standard. And with this method, you also could check what is happening with the rotor shape before and after. You can change it to run with different loads, with different active power, reactive power. So although it does not look like something very, very challenging, and you would say you can do it by yourself, it allows you a lot of flexibility to automate it and to run it on many different faults and on many different units. So it was interesting for us to see how we can do that. And the evaluation of machine learning that we were like more pleased with was with the normal behavior modeling. Here it showed us most results, and this is something that is running actually also in Croatia in one power plant as a test, as the test site. So before doing our system, we did like, let's say, we were checking what competition does and how they do. They did not call it machine learning concepts. They call it expert systems. And what kind of approaches they did. So, like standard machine condition monitoring system will be based on the thresholds. So you will say, okay, you have my machine, you have like parameters of your machine, and standard will say like zone A will be 100 microns, then 150, 200 microns, and you will set the thresholds for the alarming. And you will get alarms for that. But the thing is that that is like very fixed. Your machine is typically behaving differently in different operating conditions. It will behave differently if it's full load, if it's half load, if it's reactive, if the high water and low water are different. Your machine vibration signature will be completely different. And if you have a static thresholds, you will not be able to detect a fault in the beginning. And that's why its idea is not to have fixed thresholds for detecting your fault or like indication of your fault, but somehow to generalize it and say, okay, if I have like 100 megawatts and my upper water is completely full, I expect my vibration to be, let's say, 70 microns. And if in these kind of conditions my vibrations change to 90 microns, there is something going on. Although this 90 microns still would be below the standard threshold, let's say you have it on 100 microns. So you get the ability to detect fault earlier, and for that you need to create you have to train your system to know what is normal operating mode for each condition vector that you have. So what will actually this mean? You will measure one value and you need to select, let's say, good data set for 1 year. What we were doing wrong in the beginning, we were trying to define like faults. But for the machine learning, you need like many faults. And you typically don't have so many faults recorded. And then you have a problem. So then we switched the approach. And we said, okay, let's define what is good. And if my machine is out of this, my scope for good, I will say something is wrong. I don't have to necessarily say what actual root cause is this. I will be satisfied in the beginning that I say, okay, something is going wrong. And I then maybe try to focus on that. So after you train the model, based on the measured value, you will also have predicted value. So you will be able, this every second where you calculated a measured value, you will be able to predict what is the expected value during a period where you defined normal machine operation. And then you will check what is the residuals. And you will compare what is actual measured compared to the predicted, and you will say, okay, now I don't have a fixed threshold. I can say for this example, if my normal machine condition for some operating condition is 70 microns, and it changed to 100 microns, I have a change in 30 microns. And I can say, okay, there is something wrong, and then I will enter this, let's say, warning zone. So although like the vibration level is not like very high, you detect that there is something going wrong. And if something changes like from 100 to 110, you might say, okay, this is still good. I expect with this kind of operating conditions, I expect 100 microns. I changed for 10 microns. And it's in my expected range, you know. Although it's like nominally you have a higher vibrations than initially, your machine is good. So you will again need to have a good database. Again, a lot of data preparation, a lot of data cleaning. You have to define a good input data set. I think what we did once, we defined too broad data set, and our model was predicting the fault. So it was not detecting that there is an error because model predicted that there will be increase in the vibrations, and then there were like no notifications. So you have to really be careful not to take some time period where your fault is already happening, because then your model will be predicting fault, and you will not see residuals into that. And yeah, so now for the machine learning, there are like different models. They are like changing very, very fast. And thing that we have to take in consideration here is hydropower plants are typically of the internet connected, and you have to run everything locally. So you cannot consider to use some enormous resources from the ChatGPT, Claude, or something else. You have to select the models that will run good enough on premise, or maybe in the best case on one centralized place for the few power plants. So you have to be careful about that. And it's like a lot of testing, you know, try, and you cannot immediately say, okay, this model will be good for this. It's a lot of tries and errors, and you're just slowly learning and upgrading your experience about that. So yeah, for example, the model that we used in this example, and a lot of these models are freely available on the internet. So you can take the model, you can download it on your site and use it with your data. And for example, one of the things that was again, a lot of mining to prepare the data inputs. We have the data stored in the database in the way that you have for every timestamp. You have some signal value and actual value, and each signal ID will have different row, and for each timestamp you will have multiple signals. And the model, for example, expects to have data input defined as for one step. Okay, give me everything what I have in. So it's like a lot of let's say data scientist stuff that is not like, again, not much fun, not much interesting. You have to prepare everything to have as a proper input to the model that you selected to use. So that's unfortunately like that. As I said, a lot of mining, not all the parts of the work are so interesting. So for one, I mentioned that we have this running as a demo installation on one site. We have defined which parameters which we want to use. And we said we want to check the first harmonic of the relative vibrations on the bearings. So that was something that we wanted to define as output parameters from the model. And then again, based on the experience about the vibrations, about fault matrix, and availability of the data in the system, we have selected, let's say, few parameters that actually influence. First, of course, you want to have your machine running. You know, if it stopped, you immediately delete all that. Active, reactive power are very influencing, and temperature and water flow. So again, out of the 1,000 parameters, we have selected 6 here to predict, and I don't know, 8 that are correlating. So based on these 8 parameters, only 8 parameters from those 1,000 are used to predict this. So you use it again for the training. For the training, you use both inputs and outputs. So you say for this set of the inputs, I expect 70, 100 or whatever value. And then after the training, you just use this and you try to predict what will go on. So the model that proved suitable for us was this Random Forest Regressor. So who has more question about this model, I will ask you to write email. So that will be really specific for the Hussein to answer. But taking in consideration the amount of data, processing power, processing time, this fit was the best for us. And also we were like trying to make some estimate what are the errors in the fault. So yeah, this is running in the hydropower plant in Dubrovnik, in Croatia. It's running as a prototype. And yeah, so we have like different data sets here. And what we actually did. So there was like a major problem with the machine in 2022. So we took data from 2021, trained it on the data set that I mentioned, and they said, okay, now we have a good data set and we have a proper prediction, and then we wanted to evaluate if we could detect the fault which happened in 2022. So what we did, from the 2021, we took 6 months of data for the training, and we trained the model based on those parameters I mentioned. And the next 6 months we used to evaluate our training. And this was the result. So the prediction was like very good. We did not have unexpected behaviors for all the machine condition modes. So like 6 months of data, we were like predicting very, very fast. So this is like, maybe to explain. So this is actually a parameter that is this, what I mentioned, residual. So what is the difference between the measured value and the predicted value? And it was like, I think it was like below 5%. You know, the dissipation between the actually predicted and the measured value on the evaluation set. On the training set, you have almost 100%. So on the evaluation set, where there is a change in your data, you get like pretty good data. So then we got to the end of 2021, and we applied the same prediction method before the fault actually happened. And this is what was going on. So from this kind of residual, which your prediction completely fits the measured value, we came to this situation. So there was like small progression that your vibrations are going on, and residual is growing. And in one moment we got like that residual was like 100 microns more than we were expecting. So it means that, I mean, you see that as also that there is something is changing, but the thing is that with this method, you are not focused on the fixed threshold. You are actually comparing each machine operation mode. And when doing more analysis on different bearings, you see that behavior was different. You know, not it. Of course, the root cause was not influencing all three bearings differently. The bearing that is much closer to the root cause will have it will detect it earlier. So, for example, in this one, the progress was not so steep in the as here. So and important part is what I wanted to say. We have now we analyze like different graphs, and we came to this conclusion. For different parameters, we had different early warning times. So for let's say for the on the upward guy bearing, we also could not see it clearly, but on the turbine guy bearing, we saw the problem 14 days before it actually happened. So, and if you check the low warning, again, on the upper guy bearing, we saw it just when it was already coming and like 2 weeks before the fault. But on the turbine guy bearing, the fault was detectable 47 days. I mean, you got warning, there's something's going wrong. And then you were entering from low warning to warning, high warning, and critical. So 47, 43, 25, and at the end, 14 days. So that's the thing that by manual detection, it's not possible to achieve. And that's the goal, you know, to create some notification in this moment that will still human evaluate and say, okay, what is going on, maybe do like more deeper analysis, and it's kind of a helping tool. And this normal behavior modeling, it's possible to apply it for different parameters. This was our test set, where we used the first relative vibrations and the first harmonic, but you can, based on your fault matrix, define it for different faults and different errors that you want to detect. So, yeah, and last thing, what we tried to do, what we were playing is LLM powered monitoring. Now, everyone we are like not Googling anymore, we are like chatting with some AI bots or however it's called. And of course, users, especially younger users, want the same experience on the machine condition monitoring software. As I said, for example, that nothing changed in the past 20, 25 years with the data, but expectations from the users changed. So VESCI application from 25 years ago had the same numbers in it, but the way how you were getting that, it was not like user-friendly, it was not flexible, you have to go back and forth like many times. And today's application is showing same data, just like much faster, much more data, more user-friendly, and so on. So this is the same what will happen with LLM implementation inside of the machine learning. We expect that in the next few years, you will also want to chat with your monitoring system and say, okay, is there any, did you notice some fault on my machine? So input for that, again, this is only UI, again, for the user. So, for example, VESCI changed from the CODIS application in the lab view that was like very strict, using the same data, to the web application that is now very flexible, and probably one day we will switch to something like this. But still using the same data, same features, same ways of the extraction, just changing the experience. For this, you need a lot of power again. So the model and the platform that we used it on the University of Zagreb, and we managed to get some access to some of their server, and it was like 10,000 times less powerful than the ChatGPT used for the training, and 500 times slower than the ChatGPT that we use for the running. So that, of course, provides the inputs for the expectations. If you have something that is 500 times slower and less powerful, you cannot get the same outputs as what you get from the ChatGPT now. But that's a reality for the energy sector, especially with these cybersecurity requirements getting much stricter and stricter. You have to rely on the things that can go run on premise. We did that in 2024, and Hussein at that time selected some SQL coder model. In the 2025, there was DeepSeek and some other models that already changed the requirements for the hardware. So something that is changing very, very dynamically, but something that needs to be monitored. So, for example, this is like what will actually happen here? You will write a question to your system, and it will, for example, create a plot for you. So maybe you don't have to dig and find, let's say, if you have a rough load zone on your machine, maybe you can say, show me the data only during the rough load zone. And then the system has to be smart enough to go into the database, that detect what the rough load zone is, and prepare you the graph like this. So again, you can get this data today. It's in the database, but you have to go manually, select it, and so on. And with this system, we expect it to be able to run it. So for us, this was only the test concept. We did not continue with developing of this, but it proved that there is a potential there. We got awareness of the limitations for that. We are still focusing on the normal behavior modeling. It proved much more benefits for the user in this moment, because this early fault detection is something that you actually, that's why you have monitoring. You want to detect the fault. This, and you want to get the notification. This approach is good, but since we are like with the limited resources in a company, we kind of evaluated this, stopped here, and once when we get like some good project, we will continue and try to really implement it in some and create a demo installation. In this moment, we stop here, and yeah, normal behavior modeling really proves a lot of potential, and it's our direction where we plan to go. I think I used all the time. Do you have some questions?
Yeah, you showed us that the machine learning, you saw the damage 14 days before it happened.
Yeah.
What about if you, without machine learning, what was the time?
No one noticed, so the machine...
No, maybe...
I mean...
20 days before, you can see that the vibrations are already increased enough so that you can actually see it by, if you're looking at the data and just in the software that you have now. Tina is our user, so.
Yeah. But at the end, in the reality, on site in the power plant, no one noticed like in this way. So the fault.
No alarm came.
No, there were like alarms, but when you have alarm and everything goes on, and you again have alarm, and
maybe 20 days before it was already
for this model.
20 days before it was already they noticed.
For this model, you need to have some changes in input, because if you model only normal behavior, you need to have some change in the inputs.
No.
To system to notice that something is happening.
The outputs.
Output should detect.
Yes, but if you are modeling only normal behavior, so you have 1 year of good data.
Yeah.
The one bad data needs to come, so you have the residual growing.
Yes.
So important thing is that this wrong data is small and no one will notice it.
Yeah.
But the software.
Yeah.
This is the crucial thing.
Yeah.
If you check it every day and you notice it by yourself.
Then you don't need the machine learning system.
Yeah.
Yes, but I know.
I mean, as what I said in the beginning, in this moment, machine learning is providing tools to automate, to spread on many sites, to run continuously. humans could do all those things.
Yeah.
You know, but you need to train a good vibration expert, you need years.
Yes.
You know, you cannot train it in a few days. And then if you want to expand and scale from 1 site to 100 sites, you need years to train the experts. And this is where the benefit from the machine learning is coming mainly. You know, it's providing, and then the experts can focus really on the machines when there is something going wrong, not checking all the time what I said in the beginning. If there's nothing wrong with your machine, you don't have to pay too much attention. You want to focus on the machines that actually have problem and try to figure out what is the root cause of that. Okay, thank you for your attention. I hope